so weird. 1分6.3.1。What? This okay-ish now. Hello. Okay. Wait, is this working? Let's see what's here. 通知面板故障。Hello. Okay. I think it's time to start. And we have a bit technical issue here, but it should be fine now. Okay. Diagonalization. Okay, so my name is wrong. But anyway. Yeah. So we have our 1 week break. Hopefully everyone is having fun with the homework and not forgetting things. But let's have a small review. So I guess because this will be so we'll have our final next week, and so this class will be the last class that has final material. But the subject covered today is quite complicated, so I will later say that you only need to remember some of the results. Only the results, only the big results you will need it in the final. And you can forget the derivation, but some of the big results is pretty important, so you need to remember them for the final. And as usual, so next class on Wednesday we should have our final review. Okay, and the next Monday is final, and next Wednesday I don't know. Next Wednesday I think we might be able to do something, but I think we can. But I'm kind of busy, so maybe we'll just skip next Wednesday. Yeah. Let's see what's going on. Maybe I will decide on this Wednesday to see whether we have extra class on next Wednesday. And but anyway, it's going to be after final, so just extra material if people are interested. But anyway, okay, let's back to the material here. Okay, and let's refresh our memory a little bit. We are talking about eigenvalue and eigenvectors, and in section 6.1. We give most of the definition. Okay, so we have the definition of eigenvalue and eigenvector. It's defined for every n by n matrix. So every n by n matrix A, you can find eigenvalue and eigenvectors, where eigenvectors are the vectors that you multiply A on, that you get back to this vector x, but multiplied by another scalar lambda. Okay, so this lambda is called the eigenvalue, and x is the eigenvector. If lambda and x satisfy this ax equal to lambda x, then they are eigenvalue, eigenvector. So eigenvalue, eigenvector pair to this matrix A. Okay, and from this equation we can do a whole bunch of derivations. So you move things around, and you see that a minus lambda ix need to be 0. And then you consider this matrix A minus lambda I, then you find out that it has a non-trivial null space just because of this equation, and that means it's singular, and that means that the thing all the way back to is in chapter 2. We know that the determinant of A minus lambda I need to be 0. Okay. And then you can think about A minus lambda I as the uh, the determinant of a minus lambda I as some expression that depend on this variable lambda. Okay, so you can solve for what lambda makes the determinant of a minus lambda I equals 0, and yeah, so this is called a characteristic equation, and this determinant part, when you expand out everything, is actually a polynomial in lambda, and that's called a characteristic polynomial. Okay. And yeah, and the characteristic polynomial will have degree n, and so you have n roots for lambda. Okay. But some of the roots might be the same, some of the roots might be the same, and later we see that will give us a weird situation. Okay. And and then the next thing we talk about is a bit weird thing. So it's that we have been talking about real matrices. Okay, so the whole course we have been talking about real matrices. But even if all the coefficient of your matrix is real, we found out that the eigenvalue and the eigenvector might be complex number. Okay, so yeah, so we we need to encounter a complex number here because of solving this characteristic polynomial. Okay. And when we talk about this n degree n polynomial has n roots, which means that we're also counting the complex roots. Okay, so when you solve this polynomial equation, you can get complex roots and corresponding complex eigenvector, but A being real still give you some symmetry. That is, if you have a pair of complex complex eigenvalue and complex eigenvector, then their complex conjugate will also be a complex eigenvalue eigenvector. Okay. And here we only write the eigenvalue part, but its associated eigenvector also get complex conjugated. That's what we see when we prove this identity. Okay, so you take lambda and z, so this is eigenvalue, this is eigenvector, and you take complex conjugation of both of them. You get lambda bar, so lambda complex conjugation of this lambda equals to a plus bi, then lambda bar equals to a minus bi, and also z to the complex conjugation of z. So basically all the coordinate of z taking complex conjugation. And then this lambda bar and the z bar will satisfy a z bar equal to lambda bar z bar. Okay, that's the way to prove. And that's about A being real. And then we prove two more identity about eigenvalue and eigenvector. So they are only identify eigenvalues. So eigenvalues, the product of all of them, lambda 1 to lambda n, will equal to determinant. You can get this from this equation. And also trace of them, trace of A, which is the sum of the diagonal elements, this is sum I from 1 to n ai. Sum of all the diagonal elements of A will equal to sum of the eigenvalue of A. Okay. And yeah. Okay, so those are properties of eigenvalue and eigenvector. Then we talk about another property that's very useful for the diagonalization we are going to review next. That is, if matrix B is similar to A, then they have same eigenvalues. So if B equal to S minus 1 A S, this means B is similar to A if there is some invertible S, that you can change A to B by sandwiching A with this S minus 1 S. And if so, then they have same eigenvalues. Okay, but they will have they usually have different eigenvector unless S equal to identity. Okay, and then we talk about diagonalization. So what is the idea of diagonalization is where you want to find basically B equal to S minus 1 AS, where B is a diagonal matrix. So that is this. Okay. And yeah. Okay, but we are writing, so B is the D, but we write this in other way. So B is similar to A is also similar to B. So we want to find A that's similar to this B, but it's diagonal, so we write it as D. So we want to write A as similar to a diagonal matrix A equal to x dx minus 1 for some matrix X. And as we said, A and D are similar, so A and D have same eigenvalues, but D is diagonal. That means that means the diagonals are all the eigenvalues of A. Okay. Diagonalization, and sometimes it's possible, sometimes it's not. Okay. And then we start giving theorems that tell you when diagonalization is possible. Okay. So so first is this theorem 6.3.1 says that if all the eigenvalues are different, and then the matrix A is diagonalizable because eigenvectors are going to be linear independent, and we are going to see that matrix A is diagonalizable if all the eigenvectors are linearly independent. Okay. Or more like it has unlinearly independent eigenvectors. So more like and the non-diagonalizable matrix, as we will see in example, is that that's when you don't have n eigenvectors, basically unlinearly independent eigenvectors. You have less than unlinear independent eigenvectors, and so I guess this goes back to a bit about the roots of the polynomial. So as I said, roots of this is an n-degree polynomial. You have n roots, and we see that if the n roots are all different, then you will have basically n different eigenvectors, and this matrix will be diagonalizable. But if some of the roots are the same, then it might or might not be diagonalizable, because sometimes the roots are the same, and that make the very weird part of the space where you cannot find where so maybe you have 2 or 3 eigenvalues are the same, but 2 or 3 same roots in this polynomial, but you don't find 2 or 3 linear independent eigenvector corresponding to them. And then we see the example is okay. Let's see. I think we have an example here. The not diagonalizable matrix look like this. So it's basically like a triangular form. So if you have this matrix that has 2 eigenvalues, you solve the characteristic polynomial, it has eigenvalue 1 twice, but it actually have only 1 eigenvector. If you solve the null space, okay. So you solve for this null space, and you find out that the only eigenvector is only linear independent eigenvector is 1, 0. Okay. It's just basically only 1 eigenvector here. Okay. So yeah, so we can have a defective matrix, and it's not diagonalizable. Okay. And then we have a bit more name about this. So the number of eigenvalues, the number of eigenvalues we have a different counting. Okay. So the solving, when we think about eigenvalue as the roots of the characteristic polynomial, then there are going to be n of them, and some of them might be the same. Okay. So the same number of roots in characteristic polynomial, let's call it algebraic multiplicity. So so the other way to say you have n roots in characteristic polynomial is saying that if you add together all the algebraic multiplicity of the eigenvalues, it's going to be n. But then we define another thing, that's geometric multiplicity. That's how many linear independent eigenvector you can actually find for that eigenvalue. And as we said, this algebraic multiplicity can be different from geometric multiplicity. That means you can have more eigenvalues. So roughly that means you can have more eigenvalue than you can have eigenvectors. Okay. Okay. And yeah, so that's weird, but that's what can happen. Okay. Yeah. Oh, also something we skip is that if you diagonalize your matrix, then you can calculate this a to the some power easily, because you think about you multiply many a together, then you have a string of a together, then this x minus 1 and x will cancel out. Then so this a to the k, you can just take a and take a d to the k. Okay. And okay, so that's a small review of chapter 6. Any question? Okay. And yeah, then we go to the next part. Okay. So basically the next two parts are a little related to this difference between geometric multiplicity and algebraic multiplicity. Okay. And first 6.4, we are going to talk about a very nice set of matrices that will always have geometric multiplicity equal to algebraic multiplicity. And yeah, and actually is even a little more. So we're going to see that the symmetric matrix are always diagonalizable, and not only they are diagonalizable by orthogonal matrix. So remember, diagonalizable, you will have this a equal to x dx minus 1 for whatever x that's invertible. And we'll see that for symmetric matrix, it's not only diagonalizable, the x here is going to be a orthogonal matrix. So so remember, orthogonal matrix are matrix where all the columns or rows so I guess I say columns. So all the column vectors form an orthonormal basis. Okay, so it's a very strong constraint on this matrix, and that also means this x minus 1 will just be x transpose. Okay, so it's very nice. And yeah, so we have two theorems here. I think the first theorem we prove a little bit last time, but we can go over it once again. So yeah, so it's diagonalizable, and it has a stronger property. The symmetric matrix, all the eigenvalues are real. Okay. And yeah, so basically those two things. So all the eigenvalues are real, and okay, so here we prove the okay, so first we'll prove a weaker thing. Okay. So actually, what we are going to see in the end is that all the eigenvalues are real, and you will actually have n eigenvectors for A if A is symmetric. N eigenvalue for A, and the eigenvalues are all orthogonal. Sorry, sorry, what am I talking? Sorry. So you have n eigenvalue, and you will also have n eigenvector. As we say, it's not always true, because for defective matrix, you don't have an eigenvector. But for symmetric matrix, you will have n eigenvectors, and the n eigenvectors you can make them all orthogonal. Okay. So you can find n orthogonal eigenvector, and then from those n orthogonal eigenvector, you can form this orthonormal matrix U, and so you have this also orthogonal matrix U that diagonalize your matrix A. Okay, so it's very strong. And yeah, but yeah, and so here we are deviating from textbook, because textbook actually go to complex matrix. So they talk about Hermitian matrix, and they use even stronger property to show those. But we try to keep things simple, so we keep things in real. So we talk about only symmetric matrix here. And yeah, so this is something very nice to know. Yeah, so if people are interested enough, then maybe we'll do the Hermitian matrix. Maybe we'll do the Hermitian matrix in next Wednesday. But for now, let's see the symmetry part. I guess these two results are the thing you should remember. The proof is okay-ish. Okay. And I guess the first proof is pretty easy. The proof of first thing is we want to show for your symmetry matrix, all the eigenvalues are real. Okay. And to show that, we just need to consider this quantity. That is, yeah. A apply, so you think your eigenvalue and you have the eigenvalue and the eigenvector pair. Then you consider this quantity that's kind of sandwiching A between two eigenvectors. Okay? So you have X transpose on A and X bar. Okay? And then you can look at this thing in two ways. And then you see that this is lambda times X transpose X bar. Or if you solve this X transpose on A first, then you see this is A transpose apply on X transpose, and by A transpose equal to A, so this is just AX transpose, and then from here you get a lambda, and so this is so you resolve A with this X transpose, then you get a lambda, and so this is lambda times X transpose X bar. And the other way is you see these are the A applying on this X bar. And A applied on X bar, as we say, X bar is also an eigenvector of A with a lambda bar as eigenvalue. This is because just because A is a real matrix. And yeah, so here you get lambda bar, and also multiplying this X transpose X bar. Okay? And so you see lambda equal to lambda bar because this is norm of X is non-zero. Norm of X vector, this is non-zero. So lambda equal to lambda bar, this means lambda is a real number. Okay. Yeah. And okay. So yeah. So this is why. Yeah, so this is why the eigenvalues of A are all real. And then we can also see that now if you have a different lambda, so you have lambda 1, lambda 1, lambda 2 different, and the corresponding eigenvector equal to x1 and x2, then we can show that the x1 and x2 inner product is 0. And you will do similar things, so you still sandwiching A. So you want to sandwich A with x1 and x2, and so yeah, so you will do similar things. So you sandwich A between x1 and x2, and you try to apply A on x1 and apply A on x2, and you will get two different equations, and they are going to be the same. Okay, and yeah, so you apply. So first you try to apply A on x2. And lambda 2 is eigenvector so x2 is eigenvector of A, so you just get lambda 2 x2. So this is lambda 2 and x1 transpose with x2. Okay, and so this is basically the inner product between x1 and x2. Okay, and okay. Symmetrics. Okay, and I guess it's a bit weird. Yeah, we did. But anyway, and let's finish this first. Okay, and also we consider this again. So x1 sandwiching x1, x2 sandwiching A, and now we consider A apply on x1 transpose. And once again, you can think of this part as A transpose on x1 and parentheses transpose. N transpose equal to A. So this is A on x1 transpose. Okay. And yeah, and A on x1 it should give you lambda 1. So this is lambda 1 x1 transpose x2. Okay. And yeah. But here it's a bit funny. Okay. But anyway, then we prove that so these two things are the same, and then but you can but lambda 1 so you can move things around, and that means that either lambda 1 equal to lambda 2 or x1 transpose x2 equal to 0. But lambda 1 equal to lambda 2, so x1 transpose x2 equal to 0. Okay. And okay. So they are orthogonal, but so here it is a bit funny. But I think this is this true? think they are also real. Let's see. Okay, yeah. So something we forgot to prove here, but I guess we are short in time, so I will just claim here. That is, yeah. So it's a bit funny to say. It's pretty funny to say complex matrices are orthogonal. So, or the complex inner product is a bit different. So let's just say here what we are assuming is x1 and x2 are real. I guess. Yeah. It's real and yeah. I guess we didn't say, but you can prove that x1 and x2 real. Okay. So real matrix, then their inner product look like this. Because if it's a complex matrix, then their inner product you need to add a bar somewhere. Okay. But that's yeah. Let's just claim this is true. Okay, and yeah, so that's the first theorem. Any question? Okay, and yeah, so you see the symmetric matrix, they have a very nice property. You have these real eigenvalues, and now if you have different eigenvalues, then the eigenvectors are orthogonal. Okay, and then we next want to say is even stronger. So we want to say even you. Okay, so here is still not enough to say the matrix A is diagonalizable, because you can still have same real eigenvalues, and we still don't know the multiplicity. Okay, and the next theorem is say you will always have enough geometrics multiplicity for A such that it's diagonalizable, and it's even diagonalizable by a orthogonal matrix. Okay, so not only that you have different eigenvalues, then you have orthogonal eigenvectors. Then if you have some eigenvalue that that has multiplicity, then you will associate the eigenvectors will be associated with some space, and you can find orthogonal vectors in that space. And okay, so this is the spectral theorem. So spectral theorem has many versions. Okay, here we prove kind of the simplest version, and we prove this only for real and symmetric matrix. Okay, so spectral theorem, if you study more advanced algebra, this is talking about what things can be diagonalizable by orthogonal or unitary matrix. Okay, and yeah, but anyway, here we prove a very special case. That's for our matrix A, that's real and symmetric, and we'll try to the proof here. If you have a single note, is quite long, but I will try to give the high level idea. Okay. And yeah, the idea is kind of inductive. So we try to make our matrices smaller and smaller by finding eigenvector out and think about the race over space. Okay. I guess that's part of this. So by induction, so if n equal to 1, then obviously your A is a diagonal matrix. Okay. And then suppose for some dimension k, and then you can then this theorem is true, and then you can diagonalize your A with some orthogonal matrix U. Okay. A equal to U lambda UT, and you have a UT here because UT equal to U minus 1 is an orthogonal matrix, and lambda is a diagonal matrix. Okay. Okay. And then the induction is the idea is very simple. So suppose every n-dimensional matrix you can diagonalize. And then now consider any n plus 1 dimensional real symmetric matrix A. Okay. Any k plus 1 dimensional. Okay. And then you just pick out the eigenvalue eigenvector pair, and then you try to split the space into this eigenvector, and everything also gonna do it. Okay. And okay, so how does this go? So we have this A equal to k plus 1 dimensional, and we just say, well, okay, so if you are very careful, so there must be an eigenvalue eigenpair of A. Okay, that's because I guess you solve the you can solve the characteristic polynomial, and there must be at least one eigenvalue, right? Yeah, at least one eigenvalue. This might have a lot of multiplicity, but there will be one of them there. And then there will be at least one eigenvector associated with this eigenvalue, because you solve the null space, you can always find one vector. Okay, so you can always find at least one eigenvalue eigenvector. This is for any matrix A. Okay, and then you can normalize this eigenvector to norm 1. This just makes things a little simpler. Okay. Okay, and then then we basically think about this case. Okay, so let's think about this special case. This is a special case that makes things just show you what we are thinking. So what we are thinking is you can write A into basically a block diagonal matrix where the first dimension is this eigenvector you just find. Okay, the dimension of this eigenvector you just find, and everything else. And we are trying to say A is going to be this block diagonal form. Okay, and to show this in more concrete example, let's assume X is the easiest eigenvector, the easiest vector. It is E1 vector 1 0 0 0 0. Okay, and okay, and so we are actually skipping things here. Okay, a little slower. Okay, and so we need to show this is true. Okay, let's see, I little forgot. Okay, so AX equal to lambda. Okay, lambda E1, and what we need to show is why these are all 0. I guess where? So AE1 equal to lambda E1. So this means that all these things should equal to 0, right? Okay, and so why are these all 0? Because AE1 equal to first row equal to this first row, right? AE1 equal to lambda E1, but we can think about this matrix multiplication as the linear combination of columns of A, right? So A equal to this maybe A1, A2, A3, A, and right? So we think A as columns, and now we think about A times E1 as a linear combination of columns, and let's just pick out the first column. Okay, so this A1 equal to lambda E1 says that the first column is lambda E1, so it's lambda and a whole bunch of zeros. Okay, and then so then we know all those things are 0 here, just because AE1 equal to lambda E1, and then also we remember A is a symmetric matrix. Okay, right? So now we use that A is a symmetric matrix. So so let me try to draw this better. Okay. A is a symmetric matrix. That means if those things are 0, then those things need to be 0. Okay. So we have a 2 step. So first, so this is actually a bit non-trivial to show. But AE1 equal to lambda E1 because AE1 is the first column here, and then lambda E1 is lambda E1 is lambda 0, 0, 0, 0. So those things those things on first column should all be 0. And because those are 0, and this need to be 0 because it's symmetric. Okay. Okay. And yeah, any questions so far? Okay, I think this is the most important part of the proof. Okay. So this is the whole basis of the because these are 0 and these are 0, and you see A become a block diagonal matrix, and this basically, or this is the most important part of this proof. This will finish the induction step. Okay. Here you see that we kind of cut A equal to 2 orthogonal parts, right? So everything in this space. So in this case, you see that everything in this E1 space then is is an eigenvalue of A, and it will become lambda E1. And if you multiply A by anything on those 2 to n part, right? So you have a vector that's a 2 to n part, and you just multiply by this B. Okay. So you see that the A can be seen as a 2 orthogonal part. So on E1 part, you will multiply by lambda, and on those E2 to En part, is just multiplied by this B. Okay. So we kind of cut A into 2 parts. One part is your eigenvector x here, and then there's the rest of the part that's described by n by a k by k matrix. So remember we say this is a k plus 1 dimension. So we have this 1 dimension here, and you have a k dimension here. And we see the action of A on this k plus 1 dimensional space is kind of orthogonal. So this 1 dimension is multiplied by A, is multiplied by lambda, and the other k dimension is multiplied by B. Okay. And then basically followed by induction step. So there are a lot of detail here, but basically we're going to back to induction step. So we say B is now okay, and but there is something you need to show. So you need to show B is also real and symmetric, but easy to see just from A is real and symmetric. So B is also real and symmetric, and now B is a real symmetric matrix. Then you can use put this induction step on B. So just say B can be diagonalized by some U lambda U. Okay. So we actually call it W. Okay. So B can be diagonalized by some W D W. Okay. And yeah, so A can just be diagonalized by this 1 W. See? Yeah. So yeah. So that's basically the idea. Okay. So we want to cut the space into two orthogonal parts. The first part is the eigenvector you just find, the dimension, the eigenvector you just find, and you want to. Then the other part is the orthogonal space, the space orthogonal to this eigenvector, and then we know that A just because similar argument, and we know that A apply on those two different spaces. It will just we call, okay, so this is something we didn't say on note, but we call those two spaces invariant. Okay, so anything in this space apply A on is go back to this space because it's an eigenvector, and but anything on the orthogonal space you apply A on is actually stay in this orthogonal space. Okay, and yeah, so that's the idea, and to make this idea work is we basically map everything else to this case. Okay, and yeah, so there are a lot of detail, but what we are doing. So what if the eigenvector we found is not is E1, and and then what we do is basically we do kind of a changeover coordinate. So we will do a orthogonal rotation of A, and to make we'll find some P such that this orthogonal rotation of A, rotation or actually is more like a reflection. Okay, is a reflection matrix of A, and such that we will make this eigenvector. So after we change this coordinate, then this eigenvector become E1, and then we can back to this E1 case. Okay, and so this is really whatever we need to find some matrix that rotate X to E1, and there are a lot of matrices do this because there are a lot of freedom to do this rotation. So we want to rotate X to E1, and yeah, but the rotation basically map n orthogonal matrix to n orthogonal matrix. Okay, so you can think about what are E2, E3, En got mapped from. Yeah, and there are really a lot of freedom because you only require X map to E1. And all those things you can choose whatever, you just need to pick orthogonal. So these orthogonal matrix, they will, if you still remember the orthogonal transformation, they will basically preserve the geometry. So orthogonal things still orthogonal. So you only need to find whatever orthogonal thing in X map to those things, and it's fine. Okay, and so the rotation, or actually a reflection we find is this household reflector, and it's 10 minutes, but I think we don't need to go to the detail. But basically, what we do is so this matrix is a reflection matrix, okay, and yeah. So the matrix we construct, look at this. There is some it depends on this spatial parameter U. Okay, so you will map everything around U. Okay, so geometrically it looks like this. What is this weird? Oh, okay. So it's called V here. Okay, so it's a funny matrix. So this is a high dimensional reflector. So basically, you think about the high dimension. Maybe it's only 2 dimension here. So you think about the dimension U or V here. Okay. So this 1 minus 2 UUT thing, you will reflect around everything orthogonal to V. Okay. V and U. Okay, let's use V. So you pretend this is V here because it's just a net. Okay. So you have your matrix is 1 minus 2 VVT. Okay, and what this do is, if you think about apply V on it, then because V is a normalized vector, okay, so this V here is a normalized vector, then VTV will be 1, and so you get 1. Do we have it here? I guess let's do the calculation here. Okay, although it's not super important. Okay, yeah, but I guess the construction is a reflector is, well, it's actually something you do a lot in quantum computing, but that's a different course. Yeah, but what we want to say is 2 minus 2 VVT, 1 minus 2 VVT, apply on V, then equal to, so 1 apply on V, you get a V, and you get minus 2V and VTV. And but if V is a normalized vector, then this is 1. And so you got V minus 2V, so it is equal to minus 1V. Okay? So this is minus 1V. And the other thing you get is, but what if you get 1 minus 2V VT? Apply on some maybe V perpendicular thing. So this is a vector that's perpendicular to V. Okay, this is a bit confusing. Then you still have a 1 apply on V perpendicular. Then you get a V perpendicular. And but then this VT on V perpendicular, then by definition of perpendicular is 0, and so this is just V perpendicular. So you see that V will get a minus sign when you apply this reflector matrix on, and everything perpendicular, let's say the same. So geometrically, it will look like this. Okay, so this is V. You will reflect around like everything perpendicular to V. So if a vector apply this reflector matrix, then it's a V component get a minus sign, and everything else stay the same. So you reflect around this. Okay, and okay. So why we want to do this, because we construct a specific matrix, specific reflection matrix that reflect our x to E1. So basically, what we want to do is, I guess we can draw a more geometric picture. So we think about, we have our whatever matrix X here, and we have E1 here, right? Yeah, so we have our whatever matrix X here, and we have E1 here, and what we want to do is, then we have this E1 minus X, and then we kind of want to, so what we want to say is we want to reflect around here, and X will become E1. Okay, and yeah, so then so you do the H algebra, then you find out this U vector you actually need to reflect around, and you do calculation, and you find out that you actually reflect X equal to E1. Very nice. Okay, and yeah. So you do this change of coordinate from X to E1, and no, yeah. So you do this change of coordinate to map X to E1. So let's go back. So we make X to E1, and then we find out that in this our new coordinate, our eigenvector is once again is E1, and we can go back to this case, and we see that. In this coordinate, new coordinate, then we see that this X matrix is is kind of orthogonal to everything else A2, and you go back to this lambda B condition, and then you see that then we use our induction step, and we say that B can also be diagonalized, B orthogonal diagonalized, and and then you put all the transform of then you put all the transform of coordinate back, and then you see that, so this P transform is also okay, we usually call it H. Okay, so this H transform or P transform is also orthogonal. This is also orthogonal matrix, and then there are things that diagonalize B, that's an orthogonal matrix, and so your diagonalization is then this VT times VT times H, and but you have an orthogonal matrix times orthogonal matrix is still orthogonal matrix, and so you find out that your A can be diagonalized by this transformation to maybe your eigenvector 1 0 0 0, and then another matrix that diagonalizes the remaining B part. So so you can diagonalize your A. Okay, and so as we said, this H is diagonal, and V is diagonal, then VTH is or HTV is still diagonal, so you can just check here. So HTV, this HTV times its transpose is HTV transpose. Then you then you write all these transpose, then become VTH, and then HHT equal to identity because H is orthogonal, and then it becomes VTV, and that's still identity because V is orthogonal. Okay, and so that's for 6.4. This is about nice property of real symmetric matrix. We find out the real symmetric. Okay, so the bottom line is the thing you need to remember is real symmetric matrix are always diagonalizable, and they are diagonalizable by orthogonal matrix. Okay, And also you need to remember the the eigenvalues are real. Okay. So the results are things you should remember, and the proof hopefully you can also remember. Okay, but the results are open for final. Might or might not appear. Okay. Okay, and then I think it's a good time for a break. Then next class we are going to go very briefly about this interesting idea about singular value decomposition. Okay. Let's have a 10-minute break. today's topic. So singular value decomposition, and it's well, I guess it's a bit different from everything we talk about in this chapter because we have been talking about eigenvector and eigenvalues, and now we want to talk about singular value. So actually a bit different decomposition from eigenvalues. Okay, and anyway, so I guess. It's a bit like a generalization of eigenvalues, but we'll see in the end that sometimes it can be quite different. But anyway, so the first thing we need to notice is now we are talking about n by n matrix A. Okay. So eigenvalues, we have been talking about eigenvalues, eigenvectors, and they stay in the basically the same space. We say A is an n by n matrix, so we make the n-dimensional vector back to an n-dimensional vector. And now we want to find kind of like an eigenvalue thing, but for n by n matrix. Okay, and what we do is we basically are considering these two matrices. Okay, ATA and AAT. Okay, and so if you consider and anyway, so now we're still real. Okay, so those are real matrix and real transpose. Okay. Anyway, we consider these two matrices, ATA and AT, A transpose times A and A times A transpose. And okay, those are n by n matrices. And but if you do this thing, then you find out those two matrices are actually either n by n or n by n. I think this one is n by n and this one is n by n. Yeah. And yeah, so those are n by n and n by n matrices. And they are symmetric, okay? Because you do transpose, then you find out you get the same thing, okay? So yeah, so you get those two real symmetric matrices, and by the thing we just proved, real symmetric matrix, then they are diagonalizable, and they have a lot of eigenvalues, okay? And the eigenvalues are all real, okay? So you can find the n eigenvalue here and the m eigenvalue here. Okay, and okay, so an eigenvalue here, an eigenvalue here, and they are diagonalizable. And we're going to see that the eigenvalue here and here they are actually kind of related. So basically, the eigenvalue here and eigenvalue here are going to be the same, but you are saying there are n of them and there are n of them. How can they be all the same? And that's because there will be some of them that are the same. So basically, I guess we can spoil a little bit. So you think about A as rank R, and then you have R non-zero eigenvalue here, R non-zero eigenvalue here, and the rest of them are going to be zero. Okay. So you will have both of them will have R non-zero eigenvalues, and then you just paired with 0 to finish this M and N. Okay. So whichever M and N is larger, you will have more 0 there. And anyway, that's a spoiler, but back to the motivation. Okay, so those two things. Okay, and they are, you have a real eigenvalue, and actually you can also show the eigenvalues are non-negative. Okay, and yeah, and for example, you take just this one, and then you can think about whether its eigenvalue are negative or not. By doing the symmetry thing again. Okay, so you symmetry this thing with its eigenvalue, x and xt, and and then you find out that you symmetry it and you see the lambda xtx equal to this thing, but this thing is a positive thing. So xtx is positive because there is known square of x, and but this xt, at, ax is also positive because it's a known square of ax. Okay, and yeah, so ax squared is positive, and dividing positive is positive. Okay, and it's positive, so you can take a square root because you think a is kind of a square root of both of them, although it's although it's actually not because the dimension is different. But yeah, so you're thinking about maybe the eigenvalue of A is kind of like the square root of eigenvalue of those things. Okay? But it's actually not eigenvalue, it's called singular value. Okay? So you take the eigenvalue, square root of this positive eigenvalue, and this is what we think about as a singular value of A. And so what's the singular value decomposition? So this is actually a theorem, but we skip the proof here. So let's just state the result. So once again, we talk about any matrix. So this is actually any matrix n by n matrix, but now we still stay real. Okay. So any n by n matrix A, and okay, so here is a bit funny. So here we assume n bigger than n, but this is actually not necessary. So this is just for notation convenience. For notation, okay. This just make our notation easier. So we assume n bigger than n, but actually is any n by n matrix. There is a singular value decomposition. Okay, n by n real. Okay, so I should stress real because if it's not real, then you don't have orthogonal. N by n real matrix A. Okay, and there is always this singular value decomposition, such that A equal to U times sigma times V transpose. Okay, and yeah, and so this is quite like eigenvalue decomposition. Or I guess we never talk about eigenvalue decomposition. It's quite like the diagonalization. So you have a sigma is diagonal. Okay, so sigma look like this, diagonal matrix, and then we have and sigma. Now things are a bit funny, so we need to check the dimension. So you have n by n here, and I guess it depends on what you want to do. But here we say sigma is sigma respect is n by n here. So sigma has the same dimension as A is n by n here, and you have n by n. You have n by n orthogonal matrix before your sigma here, and you have n by n matrix after your sigma. Okay. But it's a bit funny because we have a whole bunch of zero here, right? And so we say it's a diagonal matrix, but this has a different dimension. So by diagonal matrix sigma, we mean that it has n diagonal element here, then you have a whole bunch of zero here. And this might also have some zero here, but for now, that's, yeah, we're going to see. You might also have zero in those sigma. Okay. Yeah. And, but anyway, this is a bit similar to diagonalization for the eigenvalues, but the difference, first the difference is that this is always possible, and but why is it always possible is because you are allowing more freedom here. Okay, so you see that you have a U and a V here. Okay, so you have two different matrices U and a V here, whereas in the diagonalization, so where is our diagonalization? Anyway, I guess we don't have. But for diagonalization, or maybe this thing, right? For diagonalization, you need same V or same U here. Okay. But singular value decomposition, you are allowed to use different U and V here. And allowing different U and V here make things is a lot nicer. So now you can have U and V both orthogonal. And you can also do decomposition on any matrix of any size. Okay, remember in diagonalization before we say some matrices are not diagonalizable because you might have defect. But now you will not have defect. Everything can do singular value decomposition. And yeah, so really you can get a very good form. So U and V are always orthogonal. And you can even make all your single value positive. So the eigenvalue can be positive or negative and complex number, but single value they always positive. And you can list them nicely here. So you have sigma 1, sigma 2 to sigma 1. Okay. You can have this very nice form basically because U and V are different. So whatever different order you have, you can just you can just put some permutation into your U and V, etc. I guess that's the same for eigenvalue, but anyway. But the positive thing is not. Okay. And anyway, so those sigma to sigma 1 to sigma n are called singular values. Okay, and obviously this form is called a single value decomposition. Okay, so I guess the first thing you need to remember, and that might be in the final, is that it's possible to do singular value decomposition. So the step of singular value decomposition, sometimes people forgot, but just knowing that singular value decomposition exists is very powerful. It's very good to prove all sorts of things. Okay. Yeah, but we don't have time to see more theoretical example of this. More thing about here. Okay, so why we say is n bigger than n is convenient, because we have n bigger than n here, then we can write sigma n here. Okay, so probably just from this form of the diagonal here, you can see that well, the diagonals of n by n matrix can be at most smaller of n over n. And we don't want to keep saying smaller of n over n, so we just assume n is smaller. And so we know it's up to sigma n here. Okay, right. So for example, so if we have n smaller than n, then sigma will look like this thing, right? And you have a diagonal here, and then you will see the number of sigma here is m. Okay, and it will be O0 here. Okay, and yeah. So to just make our notation a bit nicer, we assume n bigger than n, but really singular value decomposition works for any m and n. Okay. And so how you find the single values? And as we say, actually those are the single values. So singular value, you can take either one of those and just find the eigenvalues. Okay. Okay. Find the eigenvalues and taking square root. That will be your singular value. So ATA or AAT. So here we do ATA. Or actually we know n bigger than n, so let's do ATA. So we'll have less zeros. Okay. And so A is quite a singular matrix because you have two columns that are the same. So I guess just from here, then we already see something, right? Something we see is the rank of A. So remember, rank of A is the dimension of the row space or column space of A. And but the two columns here are the same, so we see the dimension of column space is only 1. So rank of A equal to 1. And so this we can keep in mind when we do a calculation. Okay. And okay, so we do ATA. We do ATA calculation, and we find out that this matrix and its rank is still just as the rank of A. But anyway, so we calculate ATA, and it is 2, 2, 2, 2 matrix. And now it's a square matrix, and we know how to do diagonalization. Okay. So yeah. So we can do the thing we have been knowing from 6.1. You can solve characteristic polynomial, etc., and you find out that the eigenvalue you have two eigenvalues. So lambda 1 equal to 4, lambda 2 equal to 0. And we didn't prove, but we can let you taking square root of those, and it will be your singular value. Okay. Okay. So singular value 1 is 2, singular value 2 is 0. Okay. And yeah. And as we said, this is corresponding to rank. So the number of non-zero singular value is equal to rank equal to 1. And that's because the rank of this thing also equal to 1. So the number of I guess we didn't say that, but anyway. Yeah. And we have a 1 non-zero singular value here. Okay, so we already find the sigma. And now it's a funny thing. So how do we find U and VT? And we say so we claim that the U and the V actually are just the U and the V here. Okay. And Anyway, so we want to find the U and the V for ATA and AAT. Okay, and so the V we can find. So okay, and so V we can find. That's the we already have ATA here, so we find the V here. ATA here, so V will have one eigenvector that corresponding to this lambda 1, 4, and another vector corresponding to this lambda 2, 0. Okay, and the result of this is this 1, 1 and 1 minus 1. But we want to make it orthogonal, so we want to normalize this to length 1, and the normalization is 1 over square root 2. So 1 over square root 2, 1, 1, 1 minus 1. Okay, this is the diagonalization of ATA. Okay. And okay, so we find our VT, and then we want to find the U, and I guess you can find the U. You can do AAT again, but here we do a bit smarter thing. Okay. Okay. So here we have a small note of how we find this A equal to U sigma VT. With A with n bigger than n. Okay, so first we calculate this ATA and we diagonalize it. So we diagonalize it, then the eigenvalues, eigenvalue taking square root, you can get the singular values, and also you find the V by the eigenvectors of ATA. Okay, and and then to find the U here. We do a bit funny thing. Okay, so we have some property here. So from here, then you can see that. So if you say you multiply V on both sides, then you see AV equal to U sigma, and also you do some transpose and move things around, then you see ATU equal to V sigma T. And why we talk about this is from this AV equal to U sigma, then you think this equation column by column. So you think this by column by column of different V, then you see that A times Vj equal to sigma j times Uj. Okay. And this equation actually have more interpretation. We hope we have time to talk about later. Okay. And okay. So yeah, so now those Vj and the Uj are actually singular vectors. Okay, and so here we kind of see what the what the singular value decomposition is really about. Okay, so we are doing this in funny order, but here you can get a feel of what it is about. This is, I guess we can compare to eigenvector equation, right? So for eigenvalue eigenvector, we have Ax equal to lambda x, right? And here, because we have different u than v, and so we get this funny equation. We get that A times v equal to sigma times u. Okay. And yeah, so so this is the singular vector, the relationship between singular vector and singular value. So you have pairs. So you have this Vj Uj pair, and A times Vj will turn equal to Uj, but time multiplying some single value sigma. And then actually the thing here is that all the different Vj and all the different Uj are orthogonal. So this is just not an arbitrary equation right here. But anyway, so with this equation, then and we already have the Vj, then you can find our Uj, right? So Avj is sigma times Uj, so Uj is just Avj divided by sigma. Okay, if your sigma is non-zero. Okay, so sigma 1 is non-zero, so we can do this. So u1 is just A times v1, so v1 is the square root of 1, 1. and divide by sigma 1. Okay. So here is your U1. And okay, so find your U1. But U is a 3 by 3 matrix. Okay. And so what's your U2 and U3, right? Remember A is so V is 2 by 2 and U is 3 by 3 because A is 3 by 2. So U is a 3 by 3 matrix, and what is your U2 and U3? Okay, and now we want to do this for U2, then you get into trouble. You find out that your sigma 2 equals 0. Okay, so sigma 2 equals 0, then you cannot divide by 0. Okay, and what does this say is actually sigma 2 and sigma 3 are kind of whatever. Okay, it's because so what happened here is because the only non-zero single value here is this 2. Okay, and it's 0 here, so basically sigma don't have any information on the other dimension. Okay, so so you have 2 here, and this 2 single value, you will correspond to some singular vector here, and but for all the zeros, then you really just need to find the 2 things that are also going to be U1, and that will be that will complete your U matrix. And but here we do it, I guess, a bit smarter. We also see that okay, so we use the second equation, and we find out that for all those HR for all those HR vectors, they actually will be the null space of AT, because from this equation, and yeah, you see that when the sigma is 0, then AT times those vector U will be 0. Okay. And so you can find the vector in the null space of AT, and so AT look like this, and you find the vector in the null space, they look like this, and you so you see that they are all orthogonal to your U1, and then you need to make them orthonormal to each other, and then you get your make them orthonormal to each other, and then you get your U. So really you have a U1 here, and then you just find whatever orthonormal thing to complete your U. And yeah, because you see that so yeah, so what I'm trying to say is, if you only consider this part, so A equal to U sigma Vt, A equal to U sigma Vt, right? So if you only consider U sigma part, this part, and these 2 vectors are really whatever, you just need to be orthogonal to this, because when you yeah, because when you multiply them, then so you can kind of do block multiplication, right? So this part will multiply on the first part, and these are all 0 here, and so here is kind of whatever. They just need to be orthogonal to satisfy U is orthogonal, because when you do multiplication, they are going to multiply on 0. Okay. And but anyway, so this is your A equal to U sigma Vt. And yeah, so we can get a bit of a geometric representation of singular value decomposition. You do some V rotation, V orthogonal rotation, it will keep the angle, and then and then you apply sigma. So sigma will stretch or compress some dimension. So the sigma, like a different dimension, will get multiplied by different sigma, and then you rotate the U rotation back. Okay. Questions so far? I guess let's talk about property of SVD, but I think, okay, for exam, then probably up to here what will be covering exam. Then later some high-level idea. But for the final, you should know. I guess the most important thing is you need to know SVD exists, and you probably want to know how to calculate SVD. Okay. Yeah. And anyway, and let's get more interpretation of SVD. Okay. And okay, so property of SVD. So we have this decomposition of A into so any matrix n by n you can decompose into this U sigma Vt. Okay, and the single values sigma 1 to sigma n are unique because we put a lot of restriction on them. So they need to be positive, and they are starting from the biggest one to the smallest one. Okay, and but the U and the V are not unique. Because just the example I say, so these two columns, so for example, the U here, these two columns are kind of whatever. You can even swap them and it doesn't matter. Okay. Okay. And okay. And so V is what diagonalizes ATA, and U is what diagonalizes AAT. Okay. Okay. So V diagonalizes ATA, and V's are the eigenvectors of ATA, and yeah, and U diagonalizes. Oh, okay. Yeah, and we can put this back. So we assume. Okay, so this is an interesting calculation. So I guess we can also do a standard derivation of why V diagonalizes ATA. Okay. So assume A already have this form. Then you can see that the AAT equal to U sigma Vt, and the AT is V sigma T Ut. And so if a single A already has this form, then we can easily see that the ATA and AAT are diagonalized in U and V, because the AAT will equal to this thing, and the VTV equal to identity. So we have U sigma T sigma T Ut. Okay. And but what is sigma T is in here? So it's a two diagonal matrix, and they multiply together. That's still a diagonal matrix. Okay. And yeah. And but here yeah. But here we are doing a diagonal matrix like I think so sigma is kind of long, and so you have sigma here, right? And it's diagonal here. So you will get a bigger diagonal matrix, and with sigma square here, and but with a whole bunch of zero here. So this sigma T matrix here. Okay. And but anyway, it's a matrix with a lot of zero, but it's still a diagonal matrix. And so you see that AAT is diagonalized by U and UT, and with diagonal being sigma T. Okay. And anyway, so the UJs are eigenvectors of AAT. And what do I say about this U being arbitrary is because you have a whole bunch of zero here, and then for the eigenvector of the zero, it has a lot of degeneracy. You can just you can find different bases for this zero space. Okay. And okay. And yeah, then the property that we already used, that is from A equal to U sigma Vt, then you can multiply V on both sides. Then you get AV equal to U sigma. Okay. And then you think about, you can look at this column by column, and you find out that AVJ equal to sigma J Uj. Okay. So this is kind of like the eigenvalue equation, eigenvector equation for singular values. And that's why the VJs are called right singular vectors, and U's are called left singular vectors. So what we think about A do is A will take the right singular vector and turn it into left singular vector, multiplying by some singular value. Okay. And yeah, and we can also take this equation and take a transpose, and so we get what do we get? So AV transpose is VTAT and equal to the U sigma transpose sigma TUT, and so you multiply V on both sides, so we move V here. So AT is V sigma TUT, and so you move the V on this side and the U on this side, so you get ATU equal to sigma V V sigma. Okay, and yeah. So you find out that this AT, then you can AT will transform this left singular value back to our right singular value. Sorry, AT will transform this U back to those V. Okay. So it's quite interesting. Okay, and yeah. So AT transform is UJ back to sigma VJ. But now we need to write this into equation because there are more UJ than VJ. Okay, so this is kind of a funny part. So there are more UJ than VJ, and it kind of corresponds to VJ equals 0. So for the extra UJ here, we just have AT UJ equals 0. Okay, because M is bigger than N. Okay, and yeah. So A transform from V to U and AT transform back U back to V, with the same sigma. Okay. Okay, and the rank thing that we say about is a spoiler. Okay, and okay, so actually the first R, single vectors, they are more useful, because they correspond to the single vector with a non-zero singular value. Okay. Okay. And so the first single vector, the V's, they will form also no basis for with this columns of AT. So but this is basically row of A. So it's about row of A. Okay. And the U's, they will form basis for columns of A. Okay. And yeah, and then you have those extra vectors. They are basis for the null space and or null space of AT. Okay. But anyway, so as we say, the rank equal to the non-zero singular values. Okay. And yeah. So and basically the rank equal to a non-zero singular value, and the rank of A will equal to both the rank of ATA and AAT. Okay. And and so if your rank is smaller than N, then we can kind of get rid of the extra part that are all zeros. Okay. So kind of back to this example, right? So the rank is 1, and we think all the extra 0 parts are kind of useless. Okay, and sometimes we'll write in this more compact form. So if it is so as in this example, so if a rank equal to 1 here, so we think how about we just take this part? So we just take this one, and we take the first singular vector and the first singular vector here. Okay. So yeah, so I think this is right. So instead of writing all 0 here, we're saying how about we have A just equal to is 1 over square root 2, 1 over square root 2, 0, and we have a 2 here, and then 1 over square root 2, 1 over square root 2. Hopefully this is correct. I think this is correct. Yeah. Yeah. So yeah, so if we cut out all the 0 part, then we can have a more compact form. Okay, and yeah, so so we only take the non-zero part, and then this is a compact form of a singular value decomposition. So we only take a non-zero part. Okay, and yeah, and this is some other form. Then we can write as the outer product. This is basically the compact form. Okay. Okay, so So that's about singular value decomposition. The properties so far. Any question? So hopefully you can give some idea about more intuition about the rank of a matrix. So rank equal to the non-zero singular vectors. Okay. And rank R matrix will transform R vectors from this n-dimensional space to R vector of this m-dimensional space. Oh, one, I guess it's okay. Yeah. Okay. And then another property of okay. Then we go back to I guess it's well back. Then let's talk a little about this. I guess this is chapter 5 thing. So remember the forbidden norm of a matrix is the known square of every element, then taking square root. Okay. And so here first we prove the property of forbidden norm is that if you multiply a matrix by a orthogonal matrix, then its forbidden norm doesn't change. That's just because the forbidden norm is so you think about forbidden norm square is the known square of every column, and every column got multiplied by this orthogonal matrix, and its known length doesn't change, and so forbidden norm doesn't change. So this is a nice matrix norm. It doesn't got changed by a orthogonal matrix, and you can also show that forbidden norm. So you multiply orthogonal matrix on front, it doesn't change, and literally you multiply orthogonal matrix on the back, it also doesn't change. Okay, and so what does this say? This says that the forbidden norm of A, you think about is a singular value decomposition, is a U sigma VT. Then it's really just is forbidden. So this U doesn't change forbidden norm, and the VT doesn't change forbidden norm. So A forbidden norm is just equal to sigma forbidden norm, and that's equal to all the forbidden norm of or the two norm of all those singular values. Okay, so I guess here you already see some theoretical application of of the singular value decomposition. So just knowing the singular value decomposition, you know, kind of know the forbidden norm of A, although but it's related to those singular values. So forbidden norm of A is this sum of a singular value square and taking square root. Okay, so that's something nice to know. And also here this is a very long theorem, but what we want to say is you want to find rank K approximation of A. Then the best thing you can do is you do a singular value decomposition of A, and you just take the first K singular value. Okay, and that will be the base K rank K approximation of A in terms of forbidden norm. Okay, so it's very nice. Okay, so this is rank K. So yeah. Okay, and so there is an approximation. So say you have a rank N matrix, you want to find a rank N minus 1 approximation, then you can get rid of the smallest singular value, and it will be a pretty good approximation, etc. Okay, and question so far? And I think I want to talk about the next example. Okay, so this is a funny example, and this shows the difference between. Hopefully it's not too confusing, but this shows the difference between eigenvalue and a singular value. Okay, and we're talking about eigenvalue and singular value like they are very similar, and really a lot of times they are similar. So for example, for symmetric matrix, the singular value will be the known square of eigenvalue, will just be a square of eigenvalue. But if you have a defective matrix like here, the eigenvalue and okay, I think in general, if you have a diagonalization matrix, then singular value are very related to eigenvalue. But you have a defective matrix, then singular value and eigenvalue will be very different. Then, so we have a defective matrix. Then we have an example here showing that the eigenvalue and the singular value can be very different. So here is the example. Okay. And okay. And yeah, so we have this huge defective matrix. It's a triangular matrix. A equal to diagonal O equal to 1, and the upper of diagonal O equal to -1, and the lower diagonal O equal to 0. Okay. And you can calculate that determinant A and determinant A -1 equal to 1, and anyway, you can calculate the eigenvalue, and the eigenvalues are all equal to 1. Okay, so it has n over 1 eigenvalue, but I think you only have one eigenvector. Okay, so this is a very defective matrix, and okay, and but even though A has all those eigenvalues equal to 1, A is actually very close to a singular matrix. That is, actually the singular value of A is not all close to 1. Okay, because you can change A a little bit. So if you just add, so you just add this very small factor, -1 over 2 to the n -2. So this is an exponential small factor where n is the dimension here. And we can show that B is the singular matrix. Okay. And yeah. So B is a singular matrix. And we can just, we have just an explicit example here. So B times this x equals 0. So B is a singular matrix, and yeah, and but B is very close A to in Fabren's law, and by the theorem we kind of skimmed through previously, and really what it shows is that A has a very small singular value. A has a very small singular value, so you can change only a little bit on it to get a singular matrix. Okay. And yeah, and well, we have just a claim here. Yeah. Oh yeah. So by the theorem, you can calculate that the smallest singular value of A is very small. Okay. Okay. So the smallest singular value here is less than this 1 over 2 to n. Okay. Because it's less than this thing. Okay. So this is the singular value of A, the smallest singular value of A. Okay. We know A is not singular, so all the singular values must be non-zero. I guess we didn't say that, but didn't prove that, but that's something true. Yeah. So A is not singular, and its eigenvalues are all very far away from 0, but it's very defective, so actually its singular value can be very small. Okay. And yeah, so be careful I guess this example shows that be careful about defective matrix. The eigenvalue and the singular value can be very different. So let's just write down here for defective matrix. Defective matrix. And lambda and sigma can be very different. Yeah. So just be a little careful. But I should still say something good for eigenvalue and singular value. So I think for the very diagonalizable matrix. So for example, for the symmetric matrix we show in the previously, this will probably, okay, let's not do this. Let's jump back. 8, 5. Okay, yeah. But for like the previous section, so for real symmetric matrix, then the eigenvalue and the singular value will be very similar. Basically, I think a single value will be just the absolute value of lambda, of the eigenvalue. Yeah. Okay. And yeah. So that's a checklist. So I guess this part we don't really need. Okay. But okay. And this is kind of don't need. And but yeah, for the single variable decomposition, the most important thing is you need to know it exists and it has this form. And so every n by n matrix it has is a equal to u sigma v, and so sigma diagonal and uv orthogonal, okay. And yeah, and whatever fundamental space we don't talk about. And but yeah, so the single values are unique, and and uv not quite. Because you have a lot of degenerates, a lot of zero space, and yeah, and you need to know have a rank R, then we better know that have rank R, then sigma has sigma has non-zero values inside, and then you have some idea to calculate about the single variable A from the ATA. Yeah, single value A, you can just calculate the eigenvalue of ATA and the AAT. Okay. And yeah. And yeah, and there is something extra. We know the for bidimensional A is the single value summation. So any question? No question, then I think that's the end of course. I guess we can do a little more proof. So the thing we can, why not? So we do a little proof here. I guess. So if A orthogonal. If A is a real symmetric, then we know A equal to U d U t. Then ATA equal to U. Wait. Okay. A is symmetric, so ATA equal to A squared. So it's just a U d square ut, and yeah, and so you see the eigenvalues of so if A is symmetric, then if A is symmetric, then ATA is just U d square ut. So you see the single values are basically here. So the single value, so the sigma is just sigma square is just lambda square, so sigma is just the eigenvalue, the absolute value of the lambda. Okay. So you see that for real symmetric matrix, then their single value is just the absolute value of the eigenvalue, so it's really related. So yeah, so if you the nicer your matrix is, the closer relation, then the single value are more representative of your eigenvalues, or I should say eigenvalues are more representative of your single values. But you have a very defective matrix, then you see a single value and eigenvalue can be very different. Okay. But bottom line is the single value decomposition exists, and you have those positive single values, and the non-zero number of them equal to your rank. And okay, so that's for class today. Any question? Otherwise, yeah, we have our final review on Wednesday. Okay, so see you on Wednesday. 题是什么？我想一下，这是这个礼拜的 U1，抱歉，我走不下来。U1、U2。Symmetric。为什么 also normal basis？ 这一题有什么问题吗？不是硬做就可以吗？那怎样？没有啊，你不是说这些在跟 vector 这些在跟 value 嘛，就把它乘上去了。应该。
但应该是我有没有看到这里有 u 乘 ut， 然后我就有点想要想它的几何意义，但我就不知道为什么这有这个问题。
几何意义，几何意义的话，其实跟之前教的那个还蛮有关系的。这个 u 乘 ut 我们是叫，如果要讲几何意义的话，应该是叫 projector， 就是会是一个投影的matrix。如果你要选的话，例如说 two dimension 的话你有一个 u 在这里，然后你的 u 乘 ut 的话，就会是说，你这样一个 matrix， 然后你乘 u 乘 ut 就会投影到这上面来，这样。可是要得到这几何意义，还是看这个数学比较容易看到嘛。这个基本上在讲这个嘛，因为 u 乘 ut， 然后你乘上 u 的话，就是今天在算那个东西嘛 ，ut 会变回 u 出来。但如果你有一个u 垂直的东西的话，那 ut 跟 u 垂直的东西乘起来变0了，那这东西就不见了。所以只有在，然后如果你是 u 垂直加 u 的话，那乘上来这垂直的 component 就会不见，然后是 u component 回来。从后面出来的、这里，就这两个东西出来的。这个我的顺序有点混乱，但是对，就是第一个是这个嘛，然后第二个是这个，所以就要推导一下。
不是上面50好像在下面的话就，
下面的话也要推下来。这样有推导，有不行吗？推导就是要上一下，应该没有太，你算一下看有没有什么你不能相信的 step。对，推导比较长一点。但其实，像我说的，其实没有很必要，你就是想办法 u， 因为那个其实没有用到的 vector 嘛，所以那你就是你想办法 u 填满就可以了。就你知道第一个 vector 在那里，那你就找两个 orthonormal 的 vector 出来就好。对。等下哪一题找好多东西。看一下。第二题的 B 跟 C 就是A 是9×6，认可是1:9。然后我们是打错了，好像要打 C 有飞。
我看答案好像也没有，也是写 R。
助教写。
啊，是助教写。
我想不起来。像我们讲的都是 C 有飞，对不对？所以我觉得应该是 C 有飞吧？是这个问题吗？
是 R of A 的话，我就觉得都怪怪的。
就我觉得是不是应该都是 C 有飞？因为他们 可能就看课本，然后没有改，因为我们跟课本 notation 不一样。所以如果是 C 有杯，你就觉得没有怪怪的吗？
对，C 有杯我觉得没有问题。
哦，那应该就是 C 有杯。
是有杯。
我在这边注掉这样一下过程。
这答案也是这样的嘛？因为我看答案也都是写 R，所以
对吧？他们的 result 超详细，然后就写 C 加 R 杯，所以应该是 C 有杯。这是哪一份呢？
真的是。
是哪个礼拜？应该是上个礼拜。好，那我讲一下，这是哪一题？然后应该都是 C 有杯。哦，可惜。你是刚才问那个问题吗？所以看懂了吗？
应该看懂，然后帮我求一个解析，就我想求量子计算，
那就修。可是我是1年开一次，那换你要等到明年了。对。
要修的话，修完但然后再修什么课？
不过现在就可以耶，我觉得演算法懂一点会比较好，但是应该可以吧？你是大几？大三可以吧？对吧？我不知道哎，还有什么微积分要会一点，那微积分你们应该也修过吧？数的部分，不过我让自己教的数学部分我都没教过。还是下礼拜，我在想下礼拜上我干脆把那个量子计算第一节的那个数学拿出来教一下，看大家多少人接受。我会给你看一下。量子计算概论，我们的数学，对吧？应该是可以。然后我找一下量子计算概论的在哪。QCO， 我先把这拔掉。是这个吗？哦，这个，对。所以线性代数其实就这种感觉，其实都在算这种东西。然后其实这个就是 vector， 然后 matrix， 然后 vector， 所以我们有 column vector， 然后 row vector， 乘以 matrix， 所以在算这种感觉的东西。对，然后 vector matrix 都是 complex value 的，所以其实接起来有点奇怪。对，所以会这样子算，但我们有不同的 notation 这样子，然后会算这种 outer product 这样子，然后 transpose， 但是因为是 complex vector， 所以我们不只要做 transpose， 要做这个 complex value 的 transpose， 对吧？就是这个我们叫 dagger 是 conjugate transpose， 然后 vector。但是 vector 比较奇怪，是我们把 column vector 换成 row vector 的时候，我们也是做 dagger， 所以 column vector 换成 row vector 的时候会加一个 i 会加符号这样子。然后 instead of real symmetric matrix， 我们有这个 Hermitian matrix 这样子。对，计算大概是这样，然后讲的都还是简单的部分。然后 eigenvalue、eigenvector。然后 inner product 其实我们也大概有教过 complex 的 inner product。然后难的部分是其实这里不太可能会教到的， 圈下去。这 polymatrix 总之就是一些 matrix。难的部分是 tensor product， 这个反正就是会教的。这个是个很难奇怪的。
Household 的 matrix 就是在 Grover 里面有到。
对啊，会有很类似的东西嘛。其实那就是做一个 reflector 而已，这样子。对啊 ，Grover algorithm 就是一直做 reflection 这样子。对啊，所以你有看过一点的话呢，应该也会看到的。就量子计算里面也会用。就还蛮多的会用 reflector 来做 algorithm 吧，因为这个是我们最会算的东西，因为它比较简单，这样，对啊，对啊，所以可能可以修修看吧。我不知道演算法的部分应该还好吧，对啊，反正你们应该有修过一些演算法之类的课，应该，应该说你们对程式有点概念，这样啦，你也是自贡系的嘛，对啊，所以是可以修修看。对啊，可以试试看。嗯哼。